Welcome back. I'm Muggsy, and today I'm going to explain how to write the chemical formula of a covalent compound. Before you learn about how to write the chemical formula of a covalent compound, you should probably know how to write the chemical formula of an ionic compound. And if you know that skill, it's actually really easy. So for instance, if I had bromine and lithium, and I were to kind of look at their valence electrons, we would see that bromine has 7, it's a halogen, lithium has 1, it's an alkali metal. In order to become stable, lithium would give up its 1 electron to bromine. In doing so, it would lose an electron and gain a positive charge. Bromine would gain an electron, gain a negative charge, and so those two equal and opposite charges would attract and form a stable ionic compound. Now here's the critical part. If we were to write the chemical formula, is it BrLi or LiBr? Which one of these two chemical formulas is it? And hopefully at this point you know that it's LiBr, because we always put the cation, the positively charged thing, first, and then we put the anion, the negatively charged thing, second. Now what if we don't have a cation and an anion? What if we have a covalent compound? And as you know by now, covalent compounds don't have charges. They don't have full positive or full negative charges. So what would we do? If, for instance, instead of lithium, I have hydrogen, and let's say bromine again, bromine's still going to have 7 valence electrons, and hydrogen's going to have 1, just like lithium. But because bromine's a nonmetal and hydrogen's a nonmetal, they're going to form a covalent bond where they share electrons versus hydrogen straight up giving its electron to bromine and making it an ionic bond. So if these two single electrons are shared, bromine has access to 1, 2, 3, 4, 5, 6, 8 out of 8 valence electrons and it's totally stable. And hydrogen has access to 2 out of 2 valence electrons and it's also totally stable because its s orbital can only hold 2. Okay, so now what do we do? Is this BRH or HBr? Which one of these two is the name? Well, it's actually basically the same rule as ionic compounds. Now remember, with ionic compounds, we put the positively charged thing, the cation, first. Now neither of these things are positively charged. If we think about the polarity of this bond and the electronegativity of the H and the Br though, there is kind of a positive charge occurring. So if I were to ask you, where are the electrons in this bond? Are they closer to bromine or closer to hydrogen? You should be able to say that they're going to be a little bit closer, or maybe a lot closer, to bromine instead of right in the middle or closer to hydrogen. And in doing so, that's going to give that bromine a partial negative charge because the electrons are closer to it. The hydrogen, it's kind of like it's given up its electrons because they're closer to bromine now, so it's going to gain a partial positive charge. This is what's known as a polar covalent bond. Now how do we know it's polar? Because if you look up bromine in the periodic table, you can see it has a really high electronegativity value. In fact, all the halogens have high electronegativity values, which is just a measure of how badly they want electrons and how strongly they'll attract electrons, because they have 7 out of 8 valence electrons. If they gain just 1 more, they'll be stable. So they're all very highly electronegative. Now hydrogen doesn't have a super low electronegativity value, but it's much lower than the halogens like bromine. So if these two were in a tug of war, bromine's going to win. It's going to attract those electrons much more strongly. So because of the polarity difference here, we do kind of have a thing that's a little bit positively charged, is acting a little bit like a cation. It isn't, but it's sort of like it. It's on the spectrum towards being a cation, and that's our hydrogen. And we do have a thing that's a little bit like an anion, and that's our bromine. So we would call this HBr. That's the correct answer and not BRH. Let me just review that one more time. When we have a covalent compound instead of an ionic compound, we can't just go with whatever's positively charged and what's negatively charged, but we can figure out what's more electronegative and in this case it's the bromine, and the more electronegative element tends to go second because it's going to attract those electrons towards it and get a partial negative charge. You could also think of it this way: the less electronegative element, in this case the hydrogen, will go first. Okay, let's do a few more examples. Here I've got some more examples of some nonmetals that are going to bond with each other to form covalent compounds. Let's take a look. So if we have sulfur and iodine, sulfur has 6 valence electrons, iodine has 7, it's a halogen. So that means if they form a single bond, that iodine will be stable, but the sulfur still won't. It'll only have 7 out of 8 valence electrons. So let's add another iodine. Boom. Now that sulfur is stable and both iodines are stable, so we have 1 sulfur and 2 iodines. Now iodine is a halogen, so we know right now it's going to be very, very electronegative. It's going to be more electronegative than sulfur, so it's the less electronegative thing, so it's going to, so sulfur is the less electronegative thing, so it's going to come first. Where will I write it? I guess I'll just write it here. And then the iodine is more electronegative, so it's going to come second, and we have 2 of them, so we'll put a little 2 subscript there, Si2, sulfur diiodide. Okay, next, if we have our nitrogen, it has 5 valence electrons, and our fluorine has 7. Again, it's another halogen. If we form a single bond there, the fluorine will be stable, but the nitrogen still won't. It'll have 2, 4, 5, 6 out of 8 valence electrons. So let's add 2 more fluorines. And have them also form single bonds. And now all 4 of these atoms will be stable. Our fluorines are more electronegative, so they're going to go second. Our nitrogen is less electronegative, so it's going to go first. So we have NF3. NF3. And in both these cases, I hope you'll notice another trend, and that is kind of the more central element tends to go first in a lot of these. That's not always the case, but that's often the case. Okay, F and Cl, this is a tricky one. So fluorine is a halogen, and chlorine is also a halogen. So if they form a little single bond here, they'll both be stable. They'll have 8 out of 8 valence electrons. Which one has the stronger electronegativity? Well, electronegativity tends to increase as you move to the right in the periodic table up until the halogens. The noble gases have pretty much no electronegativity. And then it also increases as you move up in the periodic table. So fluorine is actually kind of the king of all electronegativity. It has a huge electronegativity because it's all the way to the right, except for the noble gases, and it's all the way to the top. So fluorine and chlorine, even though they're both halogens, fluorine is more electronegative, so it's going to pull those electrons a little bit closer to itself, giving itself a partial negative charge, and the chlorine will gain a partial positive charge. So the chlorine is less electronegative than the fluorine, so it's going to go first. So this is ClF. Chlorine monofluoride is what we would call that. Remember, the less electronegative thing always goes first, for the most part. Okay, H's and O's. You probably are familiar with this example. Hydrogen has 1 valence electron, oxygen has 6. So if we form a single bond there, hydrogen's stable, oxygen isn't yet stable. Let's add 1 more hydrogen. Now they're both stable. We have 2 H's and an O. Which one of these is less electronegative? Well, hydrogen is less electronegative than oxygen, so it's going to go first. H2O. Okay. Now, all of these examples followed the rules that I told you earlier. We put the less electronegative thing first and then the more electronegative thing after that. That's not always going to be the case. There are actually quite a few examples where that rule isn't followed. So let's take a look at some of those. Okay, here's a couple more examples. We have an oxygen bonded to 2 fluorines. Oxygen is less electronegative than fluorine, so you would expect this to be OF2. In reality, it's F2O. Why is that? Well, this is a specific exception. When oxygen is bonded to a halogen, the halogen goes first. There's a lot of, the naming rules in chemistry are very contradictory because they're determined by lots of different organizations. IUPAC is kind of the biggest ones, but these often go to war with each other and have really strong opinions about how certain things should be named. And so because chemistry is a really healthy discipline with lots of different people all over the world, and they're communicating and arguing and stuff, it's not just one person dictating the rules of how it should be. There's a lot of kind of wishy-washy naming conventions and changes and stuff. So this is one of them. It's an exception. I wouldn't expect my students to know something like this. And in most chemistry classes, they're not going to get you with a gotcha question like that. This bottom one is a similar example. So if we were to look at carbon, hydrogen, and oxygen, we would determine that the least electronegative of these elements is hydrogen. So it should go first. So this should be something like H. And we've got 1, 2, 3, 4, 5, 6. H6, and then carbon, and there's 2 of them, and then oxygen. Actually, that's not right. Okay, so what if it, so let's go to the next least electronegative element, that's carbon. So C2, I guess, H6O. That's still actually not right. What we call this compound is C2H5OH, commonly known as ethanol. This is the stuff in alcohol, the kind of grain alcohol that people drink in beer and wine and spirits and all that stuff. Okay, now why do we use this naming convention instead of sticking with this kind of deal with the least electronegative element? Well, because C2H5OH is actually kind of telling me what the molecule looks like. You'll notice, by the way, that we have hydrogen in there twice. We've got H5 here and OH. So why don't we just say H6? It would actually save a lot of time and energy. Well, this OH is called a hydroxyl group. You'll notice it looks like the polyatomic ion hydroxide. It essentially is. And this is it right here. And so the chemical formula for a lot of these bigger, more complicated compounds is telling us what the compound looks like. It's 2 carbons with 5 hydrogens attached around those 2 carbons and a hydroxyl group tacked on the end, an OH. The naming convention I told you earlier kind of breaks down when we get to bigger and bigger molecules. Just like we wouldn't call this dicarbon hexahydride monoxide, we call it ethanol. When we get to bigger, more complicated molecules, we have totally new and different naming conventions we use for those, because this formula, C2H5OH, kind of helps me know immediately what the Lewis structure of this compound looks like. I don't need to worry about this. You definitely don't need to worry about this for an introductory chem course, like a high school chem course, or even maybe your first chem course in college. But it is something you're going to investigate the deeper and deeper you get into your chemistry training. So just keep in mind that there are exceptions. These are 2 of them to the rule that I taught you earlier in this video. And yeah, that's going to seem a little bit frustrating, but chemistry is the discipline of all the matter around you on Earth. So something so huge isn't going to break down into these neat little perfect rules all the time. Okay, I hope you find this instructive. It should be pretty easy to practice this skill. You should get the hang of it pretty quick. I'll see you next time.